This is one easy machine learning method that you will need to build a very reliable and high accuracy models, and it's called transfer learning. So it's basically using a pre-trained machine learning model. First, taking out the things that we need from the pre-trained model, and then also adding in some of our own elements to the model to obtain ultimate results. In this video, we show you one such example in classifying pizzas and not pizzas using this transfer learning method. Okay, so this is where we left off. We imported all the required modules, and then we got in our dataset by using the image data generator. We pre-processed the images and then visualized them. We turned that 0, 1 indicates pizza and then 1, 0 indicates not pizza. We accordingly created our model architecture and then trained the model. We first encountered overfitting, where the training data overfit the model and got a stellar accuracy of 99.32, whereas the validation accuracy stopped at around 73%. We corrected that by adding in random flip and then many dropout layers and got down the accuracy to around 75% for both. Now we're going to use pre-trained model to try and increase this accuracy more than 75%. So first I will be using the VGG16 model. This has been specifically trained for image identification and it has millions and millions of parameters. So in the first place I want to show you why VGG16 works. So let's just create another preprocessor. I'm just going to call it IDG2, which will be image data generator. And then this time I'm not going to rescale like I did for the first one, but rather than that I'm just going to mention the pre-processing function, which will be keras.applications VGG16 pre-process input. So this is the pre-processing function used by VGG16 to pre-process the images. Now let's just try that on our data. First let's just create this. Oops, I forgot to run the initial cell. Now let's just run this. So our preprocessor is ready, and I'm just going to have our train, test, and validation split once again, but this time I'm going to call it IDG2. I'm just going to copy paste it. The flow from directory function for the IDG preprocessor will apply the preprocessing onto the directory that we mentioned, which is the train part that I defined over here. And then we mentioned the target size, that is we want to reshape the size of the images to 224, 224. And then the classes, that is what are the type of images that we have to find. It should be not pizza, and then pizza we have 2 separate folders on that one. And then batch size over here is mentioned as 10, which means that each batch will contain 10 images in the train folder. Similarly, we did that for the test set, and then we also did that for the validation set, except for the fact that I also made shuffle as false, because we don't want to randomly shuffle this, as we want to evaluate the model and see how this is performing. Now this is what I copy pasted and made for our VGG16 model as well. Over here just copy pasted it and then changed this to train 2, test 2, and validation 2. But then only thing that is changed here is the preprocessing function. We applied the VGG16 preprocessing function, and that is applied to all of the images over here, which is what we see in action here. Now notice here I have kept this to be train 2, test 2, and valid 2 because I don't want to disturb the original train data that we created for our initial model. Now remember to do this each and every single time you create a new model. Don't modify the already built up model, because this is going to show you what is the difference that you made and how is it working better. Now let's just run this, and we found the images. Now let's just plot this once again and see how it is working. Then just go up here and copy paste the code that we used over here. Paste it. Now let's just run this. Now over here, this is the original images where we are using the pre-processing of our first IDG, and now I'm just going to change this to the second one that we just created and see how the pre-processing worked. And we see that all of the images are looking like this. The format of this images is better understood by the VGG16 model specifically, and now since it understands better, we get better accuracy. So hopefully that made sense. Let's just get to creating the model itself. Come over here, create VGG16 model. Now to create the VGG16 model itself, it's just very simple. First you will have to create this by using the keras applications. So it will be keras.applications.vgg16. Type in VGG16 like that. So this is the statement that you have to use to get the model itself. Just going to call this VGG16 model. Now, when the first time you run this, you have to make sure that you have an active internet connection, because it's going to install this model itself onto your computer. But then after which, you don't need to do that. You already have it installed. You can just import that as many times as you want. Just going to type in model.summary to see how many layers and parameters are available. Let's just run this. I already have this installed, so I'm just going to directly see the summary itself. And right around here, we get to see the summary itself. We see many different layers, which has many different parameters like this. And we see that it comes around half a GPU storage, and it has around 138 million parameters. So that's a lot. This is a very resource heavy model, and hence we expect it to perform well on any given data set of images. So what I'm going to do now is create our very own model, because as said earlier, we're just going to tweak the pre-trained models to our needs. So model 2 will be sequential. I'm just going to do this, and then what I will do is for layer in VGG16 model, the layers, except the last one, the last layer, I'm just going to use all of the other layers and then add them onto model 2. Model 2.add layer like that. So why am I doing this? When you look at the last layer of this VGG16 model, it will give us 1,000 different outputs. We don't need that. We only need 2 different outputs, whether it is pizza or not pizza. So what I will do is have all of the other things except the final layer and then put it onto our model 2, but then add in our very own output layer, which will consist of 2 units, and then the activation function will be softmax. But before I do that, I'm just going to also loop over all of the layers from our model 2, and then what I will do is layer.trainable equal to false. Now why am I doing this here? As right around you see here, we have around 138 million parameters that are trainable, and we don't want to train them. They are already ready for implementation. We only need our final layer, that is the output layer that we want to train, so we can just have them as it is. So make sure that you type in trainable equal to false for all pre-trained models that you use. Now since that is done, I will also add in the output layer, model2.add. I'm just going to add in a dense layer, which will consist 2 units, and then the activation function will be softmax, like that. Now let's just type in model2.summary, and we get our second model ready, and the final layer has only 2 output units, and then it has only 8194 parameters, and that is what we're going to train over here. So what I'm going to do next is compile this model, model2.compile, and then we have to mention the optimizer. I'm just going to copy paste from the before one that we made over here. Now here it's just the same thing. We mentioned the optimizer to be Atom, and then we have the loss function as categorical cross entropy, because we're using softmax as our output layer, and then we are using accuracy metric to measure how the model is performing. Now let's just train the model by using model.fit. Our training data is going to be train2 that we just created. Similarly, our validation data will be test2. Since this is a very resource heavy model, I'm just going to keep the epochs to be 5, like that, and then mention verbose to be 2. Now this itself is going to take a good while to train. Now let's just run this and wait for our model to train. First I want to show you our first model that we created. It was right around here. This is the model that we combated overfitting, and then we created the model itself. We saw that the loss value started from 0.7, and then it came all the way down to 0.52, and the accuracy was around 76% for the training data and 74% for the validation data. Now when you look at that for the tweaked pre-trained model, we see that right off the bat, we see that the accuracy is 79%, and then started off with 0.46, and for the validation accuracy, it has come down even lower. It started off with 0.22, and the accuracy is 91.2%. And it got better and better and better, and finally we see the accuracy as 95.32, and the loss has come down to 0.13, which is amazing. And then we look at that for the validation accuracy as well, which is again 95.26. Now what I'm going to do is create a prediction using this model. So ypred will be model2.predict. We mentioned the validation batches that we just created, validation 2, like that. It's valid 2, and then I'm just going to run that mp.round ypred, like that. Let's just run this. Yep, so we got all of the predictions over here. Now what I'm going to do next is import confusion matrix from scikit-learn metrics to see how this model is performing on the validation set itself. So to do this, let me just import confusion matrix, and then I will also import confusion matrix display, and just paste the code for confusion matrix like this. Now what this will do is it will give us a confusion matrix just like this, and over here the true label 0 indicates that the actual output itself is not pizza, and then the predicted label, that is the prediction made by the model, is also 0. That is, the model also predicted that the given image is not pizza, and the correct ones were 96 of them. Similarly, the predicted label is 1, and then true label 1 indicates that the actual output is pizza, and then the machine predicted that it was pizza, and these two are really high, whereas off the charts, where the actual output itself is pizza, but then the machine predicted it not pizza was 4, and the machine prediction where the image was not a pizza, but then the machine prediction was pizza is 1. So when you actually plot the accuracy score for this one, there's around 194 correct predictions out of 199. So I'm just going to run that off and then multiply that into 100 to see the accuracy. And we see that we have an accuracy of 97.5% on this model for validation set. So when you introduce new data to this model 2 that we created, where we tweaked in the pre-trained model, we get an accuracy of 97.5, which is very reliable. And all that we did was we imported pre-trained models, we looked at the available layers, and then we took all of the layers that we needed, and then we also added in some of our own layers, such as the dense layer, which we just added in as our output layer. You can add in many more layers like that, such as flatten or maybe dropout layers and many more. And then we left the model to train, and we got an accuracy of 97.5%, which is very reliable, as I said earlier. Now I also want to show you another such pre-trained model, which is called the efficient.net. Now using this way, we don't need to actually download the pre-trained model itself onto your computer. You can just install TensorFlow Hub, where all of the pre-trained models are available. We have a specific video planned for TensorFlow Hub. For now, what you have to understand is it contains a lot of pre-trained models for specific and different tasks. Now you're importing this using the URL, and then by using the Keras layer function in the TensorFlow Hub, you just pass in the pre-trained model itself and it will find it using the URL. And then you can mention the trainable as false. Just make sure that whenever you use a pre-trained model, make sure that trainable is false. You're just adding in your own layers to trainable. All of the others should be non-trainable because they are already ready for implementation. You also mention the input shape, and then you create that to the model. This was the 5th model that I created off recording. I just added in all of the layers from the URL itself, that is the efficient.net pre-trained model, and then I also added in the dense layer, mentioned the activation function, and then trained the model and got an accuracy of 95.47 over here, and then the validation accuracy went up to 96.61. Now I did the prediction, and when I came to the confusion matrix section, I saw this. So I got 197 correct predictions, and which gave us an accuracy of 98.99. So there is many different pre-trained models like this, and all of them might work for this specific case of classification of pizza and not pizza. That was just 2 pre-trained models from TensorFlow Hub, and there are many such models, and hence we decided to make a comprehensive macro guide video on TensorFlow Hub. It will be linked if it's released.